Welcome to this eLearn security video lesson on Backdooring PE Files, Part 2. In Part 1 of this video series, we introduced foundational concepts as well as created a simple backdoor in the 7-zip file manager application. Before you start Part 2, it is important that you watch Part 1 first, as we will add on to and improve techniques shown there. We will use the same version of the 7-zip file manager application that we did in Part 1, but we'll start our work on a clear, unmodified version. The backdoor that will be planted will be hidden under a legitimate functionality and additionally encrypted, so that even the majority of modern antivirus software will not be able to detect it. In the previous video, we added a custom section to the executable and stored the backdoor code there. Currently, we will try to identify unused areas within the application so that we can place the backdoor code there as well. We will also try to hide the shellcode so that it will not execute immediately after launching the program. However, we know that application functionality can be hijacked, and once used, it will run the backdoor code in the background. The last improvement to the backdooring techniques that we will cover is encryption. The backdoor code will be stored in the application in an encrypted form and will be decoded during runtime. This is another technique that will help decrease the antivirus detection rate. So our first task will be to find a place within the executable where the backdoor code can be stored. Such areas within executables are called code caves. Code caves exist in most executables and can consist of unused data or empty space within the binary. If we examine the resources section by following it in disassembly, we can see a lot of areas that contain repeating sequences of bytes that do not form any meaningful instructions, which are possibly unused. In order to identify possible code caves, we will use an automated tool called CaveMiner. CaveMiner is available on GitHub, and the installation is straightforward. To run the tool, Python 2 is required. Let's switch to a Kali Linux machine where the CaveMiner tool will be installed. We will proceed as per the GitHub page to set up the tool. CaveMiner is now ready to use from any location. Let's use it to find some code caves within the 7-zip file manager executable. The executable present on the Kali Linux desktop is the exact same copy of the file that is also present on the Windows machine. Let's type in cave_miner to go to its help message. Now let's specify the size of the code cave. We'll use a minimum size of 600 bytes, as we are not interested in smaller code caves. Immediately after pressing Enter, CaveMiner displays results. 2 potential code caves were found, both in the Resource section. The virtual address property of each cave is the address within the executable where the cave starts. We will use these addresses to inspect code caves within a debugger. The size, given in hex, describes the cave length. This is a hex number, which is equal to more than 800 decimals, which is larger than the size we specified in the search criteria. Initially, we will use the first code cave, and we'll use the second one later on. Now let's perform functionality hijacking within the executable. First, we will try to find a block of code responsible for running certain functionality. Then we will try to replace it with a jump to a code cave using the same method from video 1. Although we will not add any sections, we will still need the help of Lord PE. Since the resource section where our code cave lies does not have full permissions, we will need to alter it so we can both read, write, and execute in this section. That being said, we will check the permission boxes and save the executable. Now, X32 debug will be used to find the application functionality that will be a good subject to hijacking. To identify the desired functionality within the debugger, we need to find a reference to it. For instance, like a string that will help us to identify a unique function. Keeping that in mind, if we go to Help and select About, there is a link to visit the software homepage. If this URL address is kept within the executable as a string, this might be an easily recognizable reference. Let's go ahead and search for all string references in the executable. If we try to look for the .org domain, there is just one result, so most likely we've found the piece of code that is responsible for the Visit Homepage button. Of course, it might be possible to try to identify another functionality, but you need to keep in mind that it could be time-consuming. The easiness of finding the reference for visiting the homepage is a result of a unique string being used in it. Let's follow the URL string reference in the disassembler. We see that it is pushed onto the stack right before the call to shell execute function as its argument. Let's place a breakpoint on it by pressing F2 and navigate to the functionality in the 7-zip application. If we now press the URL address button, the breakpoint is hit, which means we properly identified the block of code behind that functionality. Now, if we run through the breakpoint, the application does the rest of its code, and the software homepage is launched. Let's copy the address of the first cave to Notepad. As we need to insert the jump to the code cave, which will replace some instructions, we will also need to save the overwritten instruction for later so it can be restored. Since the jump instruction is exactly the same size as push, we need to save just this one instruction. No additional code will be overwritten after hijacking the execution flow in that place. Let's use the binary copy utility to save the overwritten bytes. We can paste them to Notepad for later use. Another required step is to copy the address of the instruction next to the hijacked one so we can return the execution flow exactly to that place. We will also make a note of this in Notepad as a jump to the address. Let's use the address of the first cave and change the push instruction to it. No other instruction was overwritten. Let's try to use the homepage functionality once again so that we hit the breakpoint. Once done, we will move to the first code cave by using step into. The jump was successful and the execution flow is now moved into the first code cave. We land right after the FF byte, which is also an unused code. It is possible, just for better visibility, to change some of the first bytes to NOPs. This will not affect the way the backdoor works. It should be noted that the instruction in the disassembly view is what the debugger thinks is there. As a result, you might sometimes find some confusing interpretations of bytes stored in the area that is displayed in the disassembly view. Let's place another breakpoint just at the beginning of the first code cave. The first thing to do will be to save the register's state. We will use push AD and push FD instructions. We can change some of the instructions to NOPs, as they will serve as a shellcode placeholder. Let's navigate to the end of the NOP sled and create the logic that will restore the execution flow of the application. First, let's pop the registers back, then we'll perform a jump to where we left off when we were hijacking the execution flow. Also, the copied byte codes of overwritten instructions need to be restored. As the instructions are written to the executable, let's patch it and save it as another version. We will work on the updated version from now on. Now, if we press Run and allow the execution, the home page will display, and the application will work in a normal way. That means we successfully returned from our code cave. Let's disable the breakpoint since we will not use it now. This can be done by highlighting the desired line and pressing the spacebar. We can also use the homepage functionality freely. Each time it's used, the application executes our code in the background. We now need to change the NOPs to a real shellcode. Let's restart the debugger and open the newly updated executable. Before we start, let's search for our code. Since it is not in the entry point, we will use the same search reference technique to find it. Now we are looking at the beginning of the first code cave. Let's go back to the Kali Linux machine and generate the shellcode using the MSF Venom tool. Now let's copy the payload result and binary paste it, ignoring the size, into the first code cave. As previously explained in Part 1 of the PE Backdooring video series, Metasploit-generated shellcode requires some fixes, like removing the exit call at the end and also changing the weight for a single object function argument. A breakpoint is placed at the first NOP that resides right after the Metasploit shellcode finishes its execution. This way, we will have the possibility to examine the stack before we restore the registers. Let's place a breakpoint right at the beginning of the Metasploit shellcode. We'll then allow the executable to run. The netcat listener also needs to be turned on, as Metasploit will exit if it is not able to manage to establish the reverse shell. Now let's use the hijack functionality. We instantly see that our first breakpoint is reached. Let's copy the current ESP value before moving forward, as it will be needed when restoring the execution flow. We can now allow the application to run again. Once the second breakpoint is reached, we can see that the ESP value has changed. Using the calculator, we quickly confirm that the difference between the initial and the final stack pointer value is the same as in the first part of the video and is equal to 204 hex bytes. By pressing the spacebar, let's reassemble the current NOPs into the stack recovering instruction. After a single step into, we can observe the saved registers and flag being present on top of the stack. It is now possible to implement the rest of the instructions that will restore the execution flow. Once done, we patch the file and save it as another version, which we will use from now on. As soon as we allow the application to run, we confirm that all of the code was correctly implemented, as the browser window with the home page was opened while a reverse shell was received on the attacking machine. We can now close the debugger and 7-zip. In the next part of the video, we will implement an encryption and runtime decryption of the shellcode that was just added. In order to achieve it, the second code cave will be used. And this concludes our video lesson on Backdooring PE Files Part 2. Thanks for watching.